This is Miss List, and in this video, we're taking a look at AP Chemistry 2.3, Structures of Ionic Solids. A lot of what gets covered in this section is introduced in 2.2 when we're talking about lattice energy, but we give it its own section just to make sure that we cover all the bases. So, ionic solids consist of a cation and an anion. So, a cation is just the special name for what we call positive ions, and an anion is the name we use for a negative ion. That prefix "an" does mean negative, and so that's one way to remember that anions are negative. And then I always remember cations are positive, like cat paws. So cations are positive. That's a little silly joke to help you remember that. So individually and distinct ionic molecules do not exist. That is why we only really use the word molecule if we're talking about covalent compounds. For ionic compounds, we use the term formula unit. And the reason we use that term formula unit is because NaCl would be a formula unit. Well, that NaCl doesn't really exist as one Na and one Cl. What happens is not distinct set of atoms, but an array of repeating ions. And so that's what we see here in this diagram, is we see this alternating positive negative, and it repeats left and right, front to back. And this is what forms the crystal structures. If you think of little salt crystals, how they have a cube structure, that's where this comes from, is because it's this repeating array of ions. This term has a special name, and we talked a little bit about the lattice energy, and the reason that's called a lattice energy is because this is called a lattice structure, the repeating arrangement of ions. So here's some details about ionic compounds. Solids tend to be non-volatile, and they tend to have high melting points. And the reason they have high melting points is because in order to melt an ionic compound, you're going to have to separate these positive and negative ions from each other. So you have to overcome the force of attraction. This is going to require a high temperature because we know about Coulomb's law, and the closer these are together, the more energy it's going to need to separate them to overcome that force of attraction. Ionic solids do not conduct electricity because their charges are fixed in one place. So this charge of the positive cation and the negative anion, those charges are not flowing all over like we see in what's called a metallic bond. The positive and negative ions, the cation, anion, they are locked in place. They're not free to move about. However, if I was to dissolve this into water or melt it, then the ions are able to freely move about and it will conduct. But again, only if it's dissolved in water or melt in its melted phase. A regular solid ionic compound will not conduct electricity. Speaking of dissolving, many ionic compounds are soluble in water, specifically in polar solvents. We introduced the concept of polar versus nonpolar in an earlier section, but the reason for this is because if you have a polar molecule like water, it's going to have a negative end, and that will be attracted to a positive cation. There will be attraction between there, and that attraction is called an ion dipole attraction. And what that means is that the water molecule, the oxygen side of the water molecule, will be really attracted to that positive ion, and then the negative ion will be highly attracted to the hydrogen side of the water molecule. And that means it's going to dissolve a lot easier because of this ion dipole interaction. If I have something that is nonpolar, and a good example of a nonpolar solvent is benzene's nonpolar, that negative end on the water molecule or a positive end on the solvent, that doesn't exist on things that are nonpolar. So compounds don't tend to dissolve as well or at all in something that's nonpolar. Now, the strength of an ionic bond can be estimated using Coulomb's law. Remember, is the attractive force is proportional to both the charges of the ions, which means if charge increases, the force increases. So it's proportional to the charge, and it's inversely proportional to the distance. So if distance increases, force will go down. What that means is that ions with larger charges will have a larger attractive force, which leads to a stronger bond. And we mentioned this in our examples in 2.2 a little bit. Ions with smaller radii will have a larger attractive force, which leads to a stronger bond. Again, this was seen in an example that we did in 2.2 as well. But in this example, we can actually see with our own eyes that this is true by looking at the melting points. The idea here is a higher melting point indicates a stronger bond. So if I look at this comparison and I want to compare sodium chloride with sodium bromide, what do we notice here about the melting points? Well, sodium chloride has a melting point of 801, where sodium bromide has a melting point of 747. And so what we're often asked to do is to be able to explain why that is. Well, for this one, it's about the radii, because both Na and Br have a +1, -1. So it's not the charges that are different. It's going to be the radius. And it's the difference in the radius between bromine and chlorine. Bromine has a higher radius, so that means that it is going to be a weaker bond. Weaker bond means it's going to have a lower melting point, which is why that's at 747. Now, if I look at the charge effect, I can compare either of the sodium compounds with this calcium compound. Calcium and oxygen have a +2, -2. So what I've done is I've increased the charge. If I increase the charge, that means I'm going to have a stronger bond. So I can justify the fact, and that's a huge jump from 700-800 to almost 3,000. Again, an increase in the charge means a stronger bond. So a lot of times, College Board loves to ask us questions trying to explain why we see these things and why one substance's melting point might be bigger than another substance's melting point. So let's look at some examples. This one wants us to determine which would have a greater bond strength. And then it says for each set, explain your reasoning according to Coulomb's law. So for this one, they're all bonded to chlorine, and we saw a similar example earlier in 2.2. So I'm going to look at the positive cations here, and I have sodium, potassium, and rubidium. Well, remember, with Coulomb's law, distance, aka the radius, plays a role. If I increase the distance, then I'm going to decrease the force. So the one with the largest radius is going to be rubidium. So I can go ahead and get that out of that. And then between sodium and potassium is bigger. So according to this and Coulomb's law, it's going to be sodium chloride. And then I need to justify this answer according to Coulomb's law. So I would say NaCl, and I would say because sodium has the smallest radius compared to K or Rb. This will increase the attraction between nuclei, giving a greater bond strength. On this next one, we're looking at the other aspect of this. We have magnesium with fluorine, sodium with fluorine, or aluminum with fluorine. And the difference here is going to be the charge. So sodium being +1, magnesium being +2, and aluminum being +3. If we increase the charge, this is a direct relationship. I'm going to increase the force. So out of these, the biggest difference in charge is going to be aluminum with fluorine. So I would expect it to be the longest or largest bond strength. So again, I need to justify my answer according to Coulomb's law. So I would say AlF3 because aluminum has a higher charge compared. I always like to compare to everything that's mentioned compared to magnesium and sodium. This will increase attraction, giving a greater bond strength. And again, the bond strength, oftentimes we see that called the lattice energy. So for ionic compounds, we could also say it would have a higher lattice energy. Last example, C, we've got potassium with iodine or chlorine. So this seems very similar to letter A. I need the one that's going to have the smallest radius. And out of those anions, iodine and chlorine has the smallest radius there. So I would say KF. And my explanation is going to be essentially the same thing that I wrote for letter A. I'd say because fluorine has the smallest radius compared to iodine, and chlorine increases. And if I wanted to get fancy, I could say Coulombic attraction, it's giving stronger bond. Another way they like to ask this question is to have us draw a diagram. And so that's what we see in this next example. We have the structure below represents the ionic compound for KF. The first thing they want us to do is to fill in positive and negative to these circles to indicate the charges of the ions. So remember, it alternates positive. My next row, because this first one I made positive, it would have to go negative. And then the last row is going to repeat what I had on that first row, so positive. They next want me to draw an example of solid KCl. So they want me to do what they did over here in this first picture, but I'm showing a difference between K and Cl. And so what I would try to do is I would try to draw the positive ions about relatively the same size. But then what do we know about chlorine? Well, chlorine has a bigger radius. So I would actually need to draw chlorine a little bit bigger. And again, I'm doing the best I can as far as the relative sizes. And then again, we would start the second row with a chlorine. Then we'd have our potassium. Then we'd have another chlorine. And then this next row is going to repeat what we saw in the first row. So I should have a positive, then the chlorine bigger and negative, and then my positive again. The key though is the difference is that chlorine has a larger radius, and we want to make sure that we represent that in our diagram. Final example here has a comparison of boiling points. So it says using the data above and Coulomb's law, predict whether MgO would have a higher or lower boiling point than MgCl2. So here we have some official numbers. We have NAF at 1695, and then we have MgO at 3600. And remember, MgO is going to be a +2 -2. So that's going to have a larger charge because the one that we're comparing is going to be +2 with -1. So this is for MgCl2. The other thing that we want to take into account is the radius. So when I look at MgNO, Mg is the common thread. It has an ionic radius of 72 pm, and pm stands for picometers. It's a very, very small prefix for meters. I think it's smaller than nano. So micro is 10 to the -6, nano is 10 to the -9. I think pico is 10 to the -12. So the difference here is going to be in the fact that the radius for chlorine is much bigger than the radius for oxygen. So for MgO, not only is the charge bigger, but we have a smaller radius. The radius is Mg is 72 and oxygen is 140. But in the one they want us to compare it to, we've got 72 bonding to chlorine, which is a radius of 181. And so our radius is bigger for the anion, and we don't have as big a charge. So I need to explain that using Coulomb's law. And anytime they want you to compare two compounds, you need to reference both of them. So I'm going to try to do that in my example. So I'm going to say MgO will have, I'm going to state my claim first, have a higher melting point or boiling point than MgCl2. And this is going to be for two reasons. And I like a nice list. One, the charge. Charge difference is higher in MgO than MgCl2, which will increase Coulombic attraction, leading to higher melting point. Oh, I keep saying melting point, I mean boiling point, and bond strength. And then number 2, I'm going to talk about the radius. So radius is larger for Cl compared to oxygen. A smaller radius increases Coulombic attraction, increasing bond strength, leading to a higher boiling point. All right, that is all for 2.3. Again, a lot of this was talked about in 2.2. It's just a double down on some of the concepts that were introduced there in 2.2. All right, thanks for listening. All right, thanks for watching, and I'll see you guys next time.